As a maintenance manager, your responsibility primarily involves maintaining and repairing the electrical system in a reasonable manner. You are likely not personally legally liable for electrical system issues identified in a thermographic survey, provided you have fulfilled your obligations. Fulfilling your obligation involves bringing the survey results and your concerns to the attention of top management and requesting appropriate action. If top management chooses not to address the electrical issues, several consequences may arise. Firstly, there is an increased risk of electrical fires or accidents. Secondly, there can be damage to equipment or infrastructure. Thirdly, it can lead to an interruption of production. Fourthly, top management may face potential legal or regulatory liability. To effectively address these concerns, you should take several steps. 1. Document the survey results and your concerns. Create a written report summarizing the thermographic survey findings and highlighting any major abnormalities. 2. Present the findings to top management. Request a formal meeting with top management to discuss the survey results and your concerns. 3. Provide recommendations. Recommend appropriate actions to address the issues, including upgrades or repairs. 4. Follow up regularly. Monitor progress and provide updates to management. To further protect yourself, consider several actions. 1. Keep a written record of all communications regarding the electrical system issues. 2. Seek legal advice if necessary to clarify your responsibilities. 3. If management persists in ignoring the issues, consider escalating your concerns to higher levels within the organization, such as the board of directors or regulatory authorities. Now let's delve into more specifics about electrical systems and safety. A thermographic survey, also known as an infrared survey, is a non-destructive testing method used to detect thermal abnormalities in electrical equipment. These abnormalities can indicate potential problems such as loose connections, overloaded circuits, insulation degradation, or component failure. The survey involves using an infrared camera to capture thermal images of the electrical system. These images show temperature variations across the surface of the equipment. Areas with unusually high temperatures are identified as potential hotspots, warranting further investigation. Busways, for example, are crucial components in electrical distribution systems, serving as a means to carry substantial electrical current efficiently and safely. A busway system consists of a series of metal enclosures containing copper or aluminum busbars, which are conductors that carry electricity. The current carrying capacity of a busway is determined by several factors, including the size and material of the busbars, the design of the enclosure for heat dissipation, and the ambient temperature. When the current flowing through a busway exceeds its rated capacity, it leads to several adverse effects. Firstly, the temperature of the busbars increases. This is due to the increased resistive losses, or I2R losses, where I is the current and R is the resistance. Higher temperatures can degrade the insulation surrounding the busbars, leading to a higher risk of short circuits and electrical fires. Secondly, overloading can cause the busway components to expand and contract due to thermal cycling. This can loosen connections, further increasing resistance and heat. The increased resistance exacerbates the problem, leading to a cascading effect of overheating and potential failure. Thirdly, prolonged overloading can reduce the lifespan of the busway. The elevated temperatures accelerate the aging of the insulation and other components, leading to premature failure and costly replacements. To prevent busway overloading, several measures can be taken. 1. Regular load monitoring. Use clamp-on ammeters or power quality analyzers to periodically measure the current flowing through the busway. This helps identify if the current draw is approaching or exceeding the rated capacity. 2. Thermal imaging. Conduct periodic thermal imaging surveys to identify hotspots. These hotspots indicate areas of excessive heat due to overloading or poor connections. 3. Load balancing. Ensure that the electrical loads connected to the busway are balanced across all phases. Unbalanced loads can lead to excessive current in one or more phases, causing overheating. 4. Preventative maintenance. Regularly inspect and tighten connections to reduce resistance and prevent hotspots. Also, ensure that the busway is clean and free from dust and debris, which can impede heat dissipation. 5. Upgrade the busway. If the current requirements have increased over time, consider upgrading the busway to a higher capacity unit. This ensures that the busway can safely handle the increased load without overheating. When a thermographic survey reveals an overcurrent situation in a busway, it is crucial to take immediate action. 1. Verify the load. Use a calibrated clamp on ammeter to independently verify the current reading. This ensures that the initial reading was accurate and not due to a faulty sensor. 2. Identify the cause. Determine the reason for the overcurrent. This could be due to increased loads, unbalanced phases, or faulty equipment. 3. Reduce the load. If possible, reduce the load and the busway by shifting some of the loads to other circuits or by temporarily reducing production. 4. Repair or replace faulty equipment. Address any faulty equipment that is contributing to the overcurrent. This could include motors, transformers, or other electrical devices. 5. Improve ventilation. Ensure that the busway has adequate ventilation to dissipate heat. Remove any obstructions that may be blocking airflow. 6. Re-evaluate the system. Re-evaluate the electrical system designed to ensure that the busway is appropriately sized for the current load requirements. If necessary, consult with an electrical engineer to determine if an upgrade is needed. When interpreting infrared images, several factors must be considered. 1. Emissivity. Different materials have different emissivities, which is a measure of how efficiently they radiate heat. When comparing temperatures of different materials, it is important to adjust for their respective emissivities. 2. Reflected temperature. Infrared cameras measure not only the temperature of the object but also the reflected temperature from the surrounding environment. The reflected temperature can affect the accuracy of the temperature readings, especially for shiny or reflective surfaces. 3. Distance. The distance between the infrared camera and the object being measured can affect the accuracy of the temperature readings. As the distance increases, the temperature readings may become less accurate due to atmospheric attenuation. 4. Angle of view. The angle at which the infrared camera views the object can also affect the temperature readings. Measurements taken at oblique angles may be less accurate than those taken at a direct angle. 5. Environmental conditions. Environmental conditions such as ambient temperature, humidity, and wind can affect the temperature readings. It is important to consider these factors when interpreting infrared images. Regarding electrical codes and standards, the National Electrical Code, or NEC, provides comprehensive guidelines for the safe installation and maintenance of electrical systems. Several articles and sections of the NEC are particularly relevant to busways and overcurrent protection. Article 368 covers busways. This article specifies the requirements for the installation, support, and protection of busways. It includes provisions for ampacity, overcurrent protection, and grounding. Section 368.17 addresses through-wall penetrations. Busways should not be installed where they pass through walls or floors unless they are specifically designed and listed for such applications. This is to prevent the spread of fire and smoke. Section 368.28 deals with overcurrent protection. Busways must be protected against overcurrent in accordance with their ampacity rating. The overcurrent protection devices, such as fuses or circuit breakers, must be selected to protect the busway from damage due to overloads or short circuits. Article 240 covers overcurrent protection. This article provides general requirements for overcurrent protection devices, including fuses and circuit breakers. It includes provisions for the selection, installation, and coordination of overcurrent protection devices. Section 240.4 addresses protection of conductors. Conductors, including busbars and busways, must be protected against overcurrent in accordance with their ampacity rating. The overcurrent protection device must be sized to protect the conductor from damage due to overloads or short circuits. Section 240.21 deals with location in circuit. Overcurrent protection devices must be located at the point where the conductors receive their supply. This ensures that the conductors are protected from overcurrent throughout their entire length. Other relevant NEC articles include Article 110, Requirements for Electrical Installations, and Article 408, Switchboards and Panel Boards. These articles provide additional requirements for the safe installation and maintenance of electrical systems. When addressing overcurrent situations in busways, it is important to consider the selective coordination of overcurrent protection devices. Selective coordination involves selecting and coordinating overcurrent protection devices in such a way that only the device closest to the fault will trip, leaving the rest of the system operational. This is important for maintaining power to critical loads and preventing unnecessary downtime. To achieve selective coordination, several factors must be considered. 1. Time current curves. Overcurrent protection devices have time current curves that show the amount of time it takes for the device to trip at different levels of overcurrent. The time current curves of the devices must be coordinated so that the upstream devices do not trip before the downstream devices. 2. Short circuit studies. Short circuit studies should be performed to determine the available fault current at various points in the electrical system. This information is used to select overcurrent protection devices with adequate interrupting ratings. 3. Fuse types. Different types of fuses have different characteristics such as time delay and current limiting. The fuse types must be selected to achieve the desired coordination. 4. Circuit breaker settings. Circuit breakers have adjustable settings such as long time delay, short time delay, and instantaneous trip. These settings must be adjusted to achieve the desired coordination. Implementing a comprehensive electrical safety program is essential for preventing electrical accidents and ensuring the safety of personnel. The program should include several key elements. 1. Training. Provide regular training to all personnel who work with or around electrical equipment. The training should cover topics such as electrical hazards, safe work practices, and the use of personal protective equipment. 2. Lockout-tagout procedures. Implement lockout-tagout procedures to ensure that electrical equipment is de-energized before any maintenance or repair work is performed. The procedure should include steps for identifying the energy sources, isolating the energy sources, and verifying that the equipment is de-energized. 3. Personal protective equipment, or PPE. Provide appropriate PPE to all personnel who work with or around electrical equipment. The PPE should include items such as insulated gloves, safety glasses, and arc flash suits. 4. Regular inspections. Conduct regular inspections of electrical equipment to identify potential hazards. The inspection should include checks for loose connections, damaged insulation, and overloaded circuits. 5. Emergency procedures. Develop and implement emergency procedures for responding to electrical accidents. The procedures should include steps for providing first aid, calling for emergency assistance, and investigating the accident. 6. Arc flash hazard analysis. Perform an arc flash hazard analysis to determine the potential arc flash hazards in the electrical system. The analysis should include calculations of the incident energy and the arc flash boundary. 7. Labeling. Label electrical equipment with appropriate warnings and information about the arc flash hazards. The label should include information such as the incident energy, the arc flash boundary, and the required PPE. 8. Safe work practices. Implement safe work practices for working with or around electrical equipment. The practices should include steps such as maintaining a safe distance from energized equipment, using insulated tools, and avoiding wet conditions. In addition to the NEC, other standards and regulations may apply to electrical safety. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. Also, the Occupational Safety and Health Administration, or OSHA, has regulations that address electrical safety in the workplace. It is important to be familiar with all applicable standards and regulations to ensure compliance and maintain a safe working environment. Regularly reviewing and updating the electrical safety program is essential to ensure that it remains effective. The review should include an assessment of the program's effectiveness, an identification of any areas for improvement, and an update of the program to reflect changes in technology, standards, and regulations. When addressing electrical safety concerns, it is important to communicate effectively with all stakeholders, including management, employees, and contractors. Effective communication can help to raise awareness of electrical hazards, promote safe work practices, and prevent accidents. The communication should be clear, concise, and easy to understand. It should also be tailored to the specific audience. For example, management may need to receive information about the financial implications of electrical safety, while employees may need to receive information about how to work safely with electrical equipment. In conclusion, addressing electrical system issues identified in a thorough survey requires a systematic approach that includes documentation, communication with management, and implementation of appropriate corrective actions. By following these steps, you can protect yourself, your colleagues, and the company from potential legal and financial liabilities. Moreover, a proactive approach to electrical safety can help to prevent accidents, improve productivity, and ensure a safe working environment. Remember to consult with qualified electrical professionals and legal counsel to ensure compliance with all applicable codes, standards, and regulations. The electrical system can be a complex system, and it is important to properly understand the equipment, electrical theory, and how it relates to code to ensure proper operation. First of all, the electricity supply is alternating current or AC. It is produced at the power generation plant. The power plant could be powered by renewable sources such as solar, wind, or hydro, or other non-renewable sources such as gas, coal, or nuclear. Power is generated through a generator via electromagnetic induction. Power is then sent to transformers to increase voltage from kilovolts to hundreds of kilovolts to decrease losses due to transmission line resistance. The high-voltage electricity then is transmitted over many miles of high-voltage transmission lines. These lines can be supported by metal lattice towers and even wood poles. The high-voltage electricity then gets to substations near towns and cities where transformers reduce the voltage from hundreds of kilovolts to tens of kilovolts. From the substation, lower-voltage transmission lines distribute the power around towns and cities. These distribution lines are typically run overhead on utility poles or buried underground. Pole-mounted or pad-mounted transformers then step down the voltage from tens of kilovolts to utilization voltage such as 480 volts, 277 volts, 208 volts, or 120 volts. The power enters buildings through a service entrance. The service entrance typically consists of a main disconnect switch, a circuit breaker, and a meter to measure electricity consumption. From the service entrance, the power is distributed throughout the building via distribution panels and branch circuits. Branch circuits supply power to lights, receptacles, and equipment. Grounding is an essential safety feature of electrical systems. Grounding provides a low impedance path for fault current to return to the source, which allows overcurrent protection devices to quickly trip and clear the fault. Grounding also helps to stabilize voltage and reduce electrical noise. Overcurrent protection devices are designed to protect electrical systems from overloads and short circuits. Overcurrent protection devices include fuses and circuit breakers. Fuses are one-time devices that melt and open the circuit when the current exceeds the fuse rating. Circuit breakers are reusable devices that trip and open the circuit when the current exceeds the breaker rating. Circuit breakers can be reset after the trip. Electrical wiring must be properly sized for the load it will carry. The National Electrical Code provides guidelines for determining the appropriate wire size for different applications. The wire size is determined by the ampacity of the wire, which is the amount of current the wire can safely carry. Electrical enclosures are used to protect electrical equipment from the environment and to prevent accidental contact with energized parts. Electrical enclosures must be properly grounded to provide a safe path for fault current to return to the source. Electrical equipment must be properly maintained to ensure safe and reliable operation. Regular maintenance should include inspections, cleaning, and testing. Any damaged or worn equipment should be repaired or replaced promptly. Arc flash is a dangerous electrical hazard that can occur when a short circuit creates an arc of electricity through the air. Arc flashes can generate intense heat and pressure, causing severe burns, injuries, and even death. Arc flash hazard analysis is used to determine the potential arc flash hazards in an electrical system. The analysis includes calculations of the incident energy and the arc flash boundary. The incident energy is the amount of energy that a worker would be exposed to in the event of an arc flash. The arc flash boundary is the distance from the arc flash source at which a worker would be exposed to a dangerous level of incident energy. Personal protective equipment, or PPE, is used to protect workers from arc flash hazards. PPE includes items such as arc flash suits, face shields, gloves, and footwear. The level of PPE required depends on the incident energy level. Lockout-tagout procedures are used to ensure that electrical equipment is energized before any maintenance or repair work is performed. Lockout-tagout procedures involve placing a lock and a tag on the disconnecting device to prevent it from being accidentally energized. Electrical safety training is essential for all workers who work with or around electrical equipment. Electrical safety training should cover topics such as electrical hazards, safe work practices, the use of personal protective equipment, and lockout-tagout procedures. Working on electrical systems requires careful planning, proper training, and adherence to safety procedures. By following these guidelines, you can minimize the risk of electrical accidents and ensure a safe working environment.